When we think about flying, we usually picture something smooth, calm, and predictable. But what really happens when an aircraft gets pushed to its absolute limits? Today, we're going to peel back the curtain and look at the powerful hidden physics that take over right at the edge of control.
So yeah, that's the big question, right? This is the central mystery. I mean, we've all seen it in the movies, haven't we? A pilot wrestling with the controls, the plane spiraling downwards. But what's really going on there? What laws of physics can suddenly overwhelm even the most skilled pilots and the most advanced technology? Well, today, we're going to crack that code.
Okay, so to get started, you gotta understand that our basic idea of flight, the simple, elegant physics that gets you from point A to point B, that really only tells part of the story. It only applies in nice, calm, predictable situations.
So, for like 99% of a typical flight, we're talking straight and level cruising, gentle banks, smooth climbs. Engineers use these simplified models. Think of it like a really simple roadmap. And they work great. They're super useful, they're accurate, and they perfectly describe what's happening, most of the time.
But this is where things get interesting. What happens during a sudden aggressive maneuver, or when a plane ends up at a really dangerous angle to the wind? All of a sudden, that simple map isn't just missing a few side streets. It's plain wrong. The very rules of flight start to bend and break.
So that simple roadmap? It actually has a name in the engineering world, a linear model. And look, it's super important, but it also kind of hides a much more complicated and honestly more dangerous truth about how aircraft really behave when things get hairy.
So check this out. On the left, you've got the linear model. Think of that as your GPS set to highways only. It's simple, it's predictable, everything is proportional. You push the stick a little, the plane moves a little. Easy. But the nonlinear world over on the right, oh, that's the full-on topographical map, showing every mountain, every cliff, every treacherous valley. That's the world of aggressive, high-stakes flight, where the plane's reactions can become incredibly complex and totally unpredictable.
And this quote from the source material just nails it. When things get serious, those simple models just fail. So if we really want to understand what's happening at the edge, we have to ditch the highway map and start exploring that wild hidden terrain.
All right, so what are these hidden forces? What are these gremlins in the system that show up when a plane is pushed too far? Turns out there are basically three main culprits we need to investigate. Let's break them down.
First up, you've got what's called aerodynamic nonlinearity. The absolute easiest way to picture this is a stall. See, normally, air flows nice and smooth over the wing, generating lift. But if you pitch that wing up too far, that smooth flow just breaks away. The wing literally loses its grip on the air and the lift collapses. It's not a gradual thing, it's a sudden, dramatic event. And that's classic nonlinear behavior.
Okay, next up is inertial nonlinearity. And this one is awesome, it's the ice skater effect. You know how a figure skater pulls their arms in and suddenly starts spinning way faster? That's a change in their inertia. Well, for an airplane, if it's rolling really fast, that rotation can create these huge, unexpected forces in other directions. So a pilot thinks they're just doing a simple roll, and bam! The plane suddenly pitches or yaws violently in a way they never intended.
And our third culprit? Well, this one is the weirdest of the bunch, kinematic nonlinearity. This is all about the bizarre geometry of rotation itself. At really extreme angles, like, say, a plane pointing straight up, the very math we use to describe its orientation can just break. It becomes singular. The basic ideas of pitch and yaw get all tangled up, and the plane's orientation becomes confusing and unpredictable.
Okay, so we've got these three powerful, kind of spooky forces, all playing off each other at the same time. So how in the world do engineers study this stuff safely? I mean, you can't just send a pilot up and say, hey, go lose control for us. The answer? You build a perfect digital twin of the aircraft.
Right, and the key thing to get here is that these forces aren't working alone. They create this complex chain reaction feeding into each other. You can't just scribble this out on a blackboard. No way. You have to simulate the entire thing all at once inside a powerful computer.
And here's how they do it. It's called the 6 degree of freedom, or 6DOF, simulation. That's because it models every single way a plane can move through space. First, they tell the computer everything about the plane, its mass, its shape, its inertia. Then, they program in all the forces, like its unique aerodynamics and engine thrust. Next, and this is crucial, they code in the full, nonlinear equations of motion, the real rules of physics. And finally, they hit go and run thousands of virtual tests, calculating the plane's every move, millisecond by millisecond. It's like a virtual flight test without any of the danger.
All right, we've found our culprits, the three hidden forces. We've got our high-tech forensic tool, that amazing simulation.
Now, let's put it all together and solve the mystery we started with. What is an out-of-control spin?
A spin is like the ultimate example of this nonlinear world. The aircraft is falling, but it's also corkscrewing through the air, rotating like a maple seed. And what's so terrifying about it is that it can become a stable state. The plane gets locked in and actually wants to stay in the spin. And get this, your simple linear model, it would tell you a spin can't even happen. It literally can't predict its existence.
But inside that powerful simulation, we can see the whole story unfold. It's a chain reaction. It starts with a big pilot input that triggers an aerodynamic stall on just one wing. That makes the plane roll hard. That fast roll then activates those inertial ice skater forces, which create a sudden pitching and yawing motion. And finally, that bizarre kinematic geometry locks the whole thing into a stable auto-rotating descent. It's all three of our culprits working together, conspiring to trap the aircraft.
And that is why all this matters so much. The simulation lets engineers watch this entire disastrous chain reaction happen in complete safety. They can rewind it, they can tweak the variables, they can test out solutions. This lets them build safer planes that are harder to spin in the first place, and it helps them write the exact emergency procedures that pilots train on to save lives.
So at the end of the day, that's the big takeaway. The simulation is the bridge. It's the thing that connects the clean, simple theories of everyday flight with the messy, dangerous reality of what can happen at the absolute limits. It is, without a doubt, one of the most important safety tools in all of modern aviation.
And that kind of leaves us with one last big question, doesn't it? We've seen how flight is secretly governed by these hidden, nonlinear rules that only pop up at the extremes. It really makes you wonder, what other big, complex systems out there, from financial markets to the climate, are also being driven by powerful, nonlinear effects that we just don't see in our day-to-day lives? And what happens when those systems get pushed to their limits?